Good morning everyone. Today I Aditya from BSc Chemistry Honors first year is today here for explaining the chapter Electrochemistry for visually impaired student. Let's start with the part 1, that is electrolytic conduction and transport number. The electrolytic and metallic conductor and its factor affecting them. The electrolytic and metallic conduction. Substances which allow electricity to pass through them are known as conductors, whereas substances which do not allow electricity to pass through them are known as insulators. Conductors are divided into two classes: those which conduct electricity without undergoing any decompositions. These are known as electronic conductors, for example, metals, graphite, and certain minerals. As the name indicates, the conduction in this case is due to the flow of electrons. Those which undergo decomposition when current is passed through their aqueous solution or melt, these are known as electrolytic conductors or electrolytes. Example: solution of acid, bases and salt in their water and fused salts, etc. The electrolytes are further classified into two main categories such as strong electrolytes and weak electrolytes. Strong electrolytes are the substances like the strong acid, which are HCl, HNO3 or H2SO4, etc. The strong bases, example NaOH and KOH, etc., and most of their inorganic salts. These dissociate almost completely in their aqueous solution or in the molten state and hence conduct electricity to a large extent. The weak electrolyte are the substances like the weak acid, for example, acetic acid, hydrine, H2CO3, and phosphoric acid, and weak bases such as ammonium hydroxide, calcium hydroxide, and the aluminium hydroxide. They have very low degree of dissociation and hence conduct electricity to a small extent. The substance like sugar, urea, etc., the solution of which do not conduct electricity are known as non-electrolyte factors which are affecting the electrolytic conduction. The conductance of the solution of an electrolyte depend upon the following factors: the interionic attractions, which depend upon the interaction between the ions of the solute and hence are known as solute-solute interaction. On this basis, the substances are classified as strong electrolyte and weak electrolyte as mentioned above. Second, the solution of ion, which depends upon the interactions between the ions of the solute and the molecules of the solvent, hence are known as solute-solvent interactions. The strong electrolyte are almost 100% ionized in the aqueous solution, whereas the weak electrolyte are the less than 10% ionized in their aqueous solution. However, there are many electrolytes whose behavior is intermediate between a strong and weak electrolyte. Hence, their dissociation is less than 100% but greater than 10%, and similarly their conductance is less than that of strong electrolyte but greater than that of weak electrolyte. Such electrolytes are known as intermediate electrolyte. Example: orthochlorobenzoic acid, orthonitrobenzoic acid, and cyanoacetic acid. Alternatively, the factors on which the electrolytic conduction depend are as follows: the nature of electrolyte. The strong electrolytes ionize completely in their the solution and hence conduct electricity to a large extent, whereas the weak electrolyte ionize to a small extent and hence conduct electricity also to a small extent. The nature of solvent. The electrolytes ionize more in a polar solvent, hence greater is the polarity of the solvent, greater is the ionization, hence greater is the conduction. The concentration of the solution. Higher the concentration of the solution, less is the conduction. This is because in a weak electrolyte the ionization is less than, whereas in a strong electrolyte the interionic attractions are higher at their higher concentration. With dilution, the interionic attraction decrease and hence the conduction will increase. Temperature. On increasing the temperature, the dissociation increases, hence the conduction increases. The difference between the metallic and electrolytic conductors. The metallic conductors are the flow in which the flow of electricity take place without the decomposition of the substance, whereas in electrolytic conductors the flow of electricity take place accompanied, accompanied by the decomposition of the substance like the electrolyte. In metallic conductors, the electrical conduction decreases with the increase of temperature, whereas in the electrolytic conductors, the electrical conduction increases with increase of temperature. In metallic conductors, the resistance offered by the metal is due to the vibrating kernels, whereas in the electrolytic conductors, the resistance shown by an electrolytic solution is due to the factors like interionic attraction, viscosity of the solvent, etc. The electric substance offer resistance to the flow of the electricity to a small or large extent. The law that gives the exact value of the resistance is known as Ohm's law. If to the end of a conductor, if the voltage E is applied and a current I is passed through it, then the resistance of the conductor is E upon I. In addition to the metals, graphite and certain minerals also conduct electricity due to the presence of electrons in them. Hence, they are collectively known as electronic conductors. The current is generally measured in the ampere, whereas voltage is measured in the volts. If 1 ampere current is flows through the conductor, when a voltage of 1 volt is applied, if the resistance of the conductor is taken as 1 volt, so thus the Ohm's law will be ohms equal to volt upon amperes. In terms of SI unit, ohm is equal to kilogram meter square per s cube and a cube. This is explained below. The specific equivalent and molar conductivity, conductances and relation among them. The specific conductance, or simply the conductivity. It is observed that the resistance R of a conductor is directly proportional to the length of the conductor and inversely proportional to the area of cross section, where P is the constant of proportionality called specific resistance or resistivity. Its value depends upon the material of the conductor. The reciprocal of the resistivity is known as specific conductivity or simply conductivity. It is denoted by the K, that is kappa. Thus, if K is the specific conductivity and C is the conductance of the solution, then R is equal to 1 upon C and the rho is equal to 1 upon K. The specific conductance or the specific simply called conductivity of a solution is defined as the conductance of solution of 1 centimeter length and having 1 square centimeter area of cross section. Alternatively, it may be defined as conductance of 1 centimeter cube of the solution of the electrolyte in the figure 2.1, or in the term of SI base unit, it is defined as the conductance of 1 meter cube of the conductor. The equivalent conductance or equivalent conductivity. For comparing the conductances of the solution of different electrolyte, it is essential that the volume of the solution should be same. They must contain the such definite amount of the electrolyte which give ions carrying the same total charge. The best choice is therefore to consider the solution having equal volumes and containing their corresponding gram equivalent masses. The conductance of the solution is called equivalent conductance. Hence, equivalent conductance of a solution at the dilution V is defined as the conductance of all the ions produced from 1 gram equivalent of the electrolyte dissolved in V centimeter cube of the solution when the distance between the electrodes is 1 centimeter and area of electrode is so large that whole of the solution is contained between them. It is represented by the lambda equivalent. The relationship between the equivalent conductance and specific conductance. The equivalent conductance of a solution is usually not found directly, but it is calculated from the specific conductance. relationship between the equivalent conductance and specific conductance may be obtained as below. Consider a rectangle vessel with its opposite walls with 1 centimeter apart and made of some metal sheet so that they can act as electrodes. The case 1, suppose 1 centimeter of the solution contain 1 gram equivalent of the electrolyte is taken in the vessel. The conductance of this solution will be then specific conductance. Further, if 1 centimeter cube of the solution taken 1 gram equivalent of the electrolyte, the conductance of the solution will be its equivalent conductance. The molar conductance or molar conductivity. The molar conductance of a solution is defined in a manner similar to that of equivalent conductance as under. The molar conductance of a solution at dilution V is the conductance of all the ions produced from the 1 moles of electrolyte dissolved in V centimeter cube of the solution when the electrodes are 1 centimeter apart and the area of electrodes is so large that the whole of the solution is contained between them. Here, the relationship between molar and specific conductance is the lambda m is equal to kr at times V. Here, the Kc is equal to 1000 upon molarity. Units comparing with the equivalent conductance, the SI unit of equivalent molar conductance will be ohm inverse centimeter square mole inverse or S centimeter square mole inverse or ohm inverse centimeter square mole inverse. Measurement of electrolytic conductance, specific conductance, equivalent conductance, all molar conductance. Electrolytic conductance. Conductance is the reciprocal of resistance, hence the conductance can be obtained by the measurement of the resistance and later can be found by the principle of Wheatstone bridge as shown in figure 2.3. The most serious problem in the measurement of resistance of the solution of electrolyte is that the direct current is used. It causes electrolysis of solution. As a result, the concentration of electrolyte near the electrode changes and this results in the change in the resistance of solution. These effects are known as polarization effects. To overcome this problem, a alternating current in audio frequency of range 550 to 5000 cycles per second is used. However, the alternating current is used. The ordinary galvanometer fails to detect the null point. Hence, galvanometer is replaced by the earphone. Further, to minimize the polarization effects, the electrodes are coated with platinum black. That is to some of the 3 modifications required in the usual Wheatstone bridge. Our source of the direct current is replaced by the source of alternative current. Galvanometer is replaced by the earphone and the electrodes of the cell are coated freshly with platinum black before use. The specific conductance or cold conductivity is related to conductance according to the expression K is equal to C multiply 1 upon A, where 1 upon A is equal to the cell constant. The equivalent conductance. Equivalent conductance is equal to lambda equivalent is equal to related specific conductance. According to the equation, the lambda equivalent is equal to K into 100 upon C equivalent, or K is equal to 100 upon normality, where C equivalent is the concentration of the solution in gram equivalent per liter. Molar conductance. The molar conductance is related to the specific conductance according to the relation lambda m equal to K into 1000 upon molarity, where Cm is equal to the molar concentration. Thus, knowing molar concentration C and specific conductance K, the lambda m, that is molar conductance, can be calculated. The conductivity water. For accurate units, the solution should be prepared in a specially purified water whose own conductance is very small. Thus, water is cold conductivity water. It is obtained by distilling good distilled water to a little potassium permanganate paramagnet has been added. Water of this type has a specific conductivity of about 8 into 10 to the power minus 7 ohm inverse centimeter inverse. Alternatively, to get the resistance of the electrolyte, the resistance of the water used for making solution may be determined and then subtracted from the resistance of solution. Thank you.